Hey everybody, welcome to the JPL Caltech Virtual Summer School on Big Data Analytics here in September from the 2nd to the 12th in 2014. I'm Chris Mattman. I'm going to be lecturing about a really interesting topic, which is understanding software architecture within the context of big data or big data architecture and its fundamentals. So the next set of slides is broken up into a series of the 3 talks, so I'll stop sort of at the end of each set of the talks, giving you time to sort of review the materials and what's going on. So let's go ahead and pop into it. We're going to cover a variety of topics in this lecture. We'll start out just giving you a basic introduction to the field of software architecture and software engineering research as it pertains to big data. I'll talk to you guys about architectural styles, the difference between styles. I'll talk to you about patterns and reference architectures. This is a little bit more advanced topic. And then we'll kind of get into some other areas within software architecture in terms of architectural modeling, visualization. How do we represent things like components and connectors as models? How do we visualize them? We'll get into some other processes in terms of drift and recovery. What happens when your code actually drifts away from your sort of intended architecture, and how do you reconcile that? And then the latter part, the last sort of third of the lecture, is going to cover a case study on understanding software architecture within the context of grid computing. So how can you actually apply this? So this first lecture here is going to go ahead and cover an introduction to software architecture and then styles, patterns, and reference architectures. So who's talking to you right now? Let me give you a little bit of background sort of on myself. My name is Chris Mattman. I sort of wear 3 hats. I'm the chief architect of the Instrument and Science Data Systems section at the Jet Propulsion Laboratory at California Institute of Technology. I have a team of about 20 data scientists at JPL, and what they're doing is working across various projects from DARPA and defense investments, building out open source solutions for Earth science remote sensing missions. We work within the context of astronomy projects, specifically the Square Kilometer Array, and its 700 terabytes of data per second that it's going to generate when it's online. So a wide variety of things. And those data scientists, the software that they're building has sort of a dual role. Every piece of software that my team writes, every line of code at JPL that my team develops is contributed to the Apache Software Foundation. Apache is a 501c3 nonprofit organization. It's also home to the world's most deployed and used web server, the Apache web server, but also home, relevant within the context of here in our Big Data Summer School, to things like Hadoop, which is the de facto big data technology in terms of processing right now. It's also home to emerging big data technologies like Spark and Shark and Mesos, which are basically these sort of in-memory data analytics. And so you should be interested in those types of things if you're interested in big data. So those software that we contribute to at Apache, where I'm on the board of directors, is also what I use to teach to other students. I'm also a professor at the University of Southern California in the computer science department there. And I teach 2 classes, one in search engines and information retrieval, big surprise, and then, which I'll be lecturing to you guys later on during this summer school here at Caltech. And then another class in, another big surprise, software architecture, which is what I'm going to cover today, software design. So they're both graduate classes. Some of them are available remotely as well. I encourage you to reach out to me, and I'll mention that sort of during the remainder of my lectures here for you guys today. So some quick notes on this lecture. The talk is definitely optimized for breadth and not depth, and that's for a reason. I'm going to try and give you the history and the applicability of software architecture to big data, which software architecture in terms of the software engineering research community has a pretty storied history over the past 20 years. It has a golden age, a heyday, things like that. There's no way in a 45-minute lecture cut into 3 that I'm going to be able to cover the entire sort of depth of some of these topics. So I'm going to point you in areas to things, give you sort of a breadth of that, and where I don't cover something, I'll be sure in the middle of the lecture and the topic to kind of point and say, hey, you might want to look here for further research. And I have a slide sort of at the end that has some pointers to future research at the end of the 3rd lecture here. You might also want to take a look at the syllabus for my USC software architecture class, CSCI 578. The link there is right there on the slides for you guys, so have a look at that, and you can get slides and other things to download to get some of the depth in some of these topics that I'm going to cover. So in other words, if you really are interested in architectural modeling, in terms of what I'm going to teach you guys about today, and you don't get enough, you're really interested in architecture description language and things, you want to look that up, take a look at the syllabus here that's linked right here, my USC syllabus, and it ought to help you. And then I just encourage you, I'm really open, send me an email. My email address is right here on the slides, or contact me on Twitter. You can probably find me on Facebook, Google+, LinkedIn. It's not a lot of places that you can't find me. In an IRC chat room somewhere, so see if you can find me, and I'll do my best to help if you can kind of connect with me here after the class. And we really welcome you here to Caltech for the JPL Caltech Big Data Virtual Summer School. Okay, so let's get started with some actual material, software architecture, and why do you care? So you care about it because the way that you design your system, even before you make technology choices, has a lot of applicability to the way that your software and your big data system is going to sort of come out the other end. If you've ever heard of the analogy garbage in, garbage out, and it has a lot more to do with what stack you pick, what big data technology you're deploying, than in terms of the way that you're actually thinking about the design of your system. There's a lot of analogies to building architecture. When we construct a building like the one that I'm presenting here to you guys in, we don't start out by simply laying copper wire and laying the plumbing and things like that without having sort of a detailed plan. And so it's just the same is true in software. It's really important. All software architectures have some software architecture, whether or not it's implicit in the design. Even if you start coding, believe it or not, there's a software architecture in your mind when you're doing that, or explicitly described. Okay, so there's a lot of analogies, here. And there's some other sort of tangential analogies and differences between building architecture and software architecture. One of them that's really obvious and really important too is that buildings and building materials are malleable. You can touch them. They're tangible. You can change them. The impact, for example, if you decide that a room should be of a certain height and depth and width, and the impact very quickly if your measurements or if your thoughts about that in your design were wrong from an engineering and construction perspective. For example, a door won't fit where you intended it to go. In software, that's not exactly the same scenario. You don't really have that understanding. Software is not tangible. You can't touch it. It's not clear to us sometimes the impact of our decisions, even at the design level, but at the implementation level as well. But even more so the design level. Before you start coding, if you're just simply thinking about what's the impact of if I pick a request-reply protocol here in my big data architecture, and what type of downstream impact will it have on data dissemination, versus if I picked a peer-to-peer type of data communication protocol and things like that. So the impact of some of these decisions isn't as sort of obvious. So even though software architectures are related to building architectures and tangible materials give us a lot more sort of testability and coverage and thoughts than software, which is why this isn't a science exactly yet, and a lot of it is based on the ability of software to be tested, have adequate test coverage, and to have an adequate architectural model that effectively represents what you're actually implementing. Okay, and so we'll talk about that during the remainder of the lecture. Software architecture has sort of enjoyed at least 20 years of sort of fundamental research. Some of the early research on software architecture was done by Dwayne Perry and Alexander Wolf in 1992, and they had a sort of seminal paper called The Foundations for the Study of Software Architecture that they published in Software Engineering Notes, which is an ACM publication, or SEN. And basically what Perry and Wolf will tell you is that software architecture really boils down to thinking about the design and thinking about the design of software and software as elements, form, and rationale. And what they're talking about there are the elements of your software system in the form of components, the units of computation, the form, the way that you put those components together, and the rationale for doing so. Why did you pick this number of components to decompose and break your software system down into? Why did you pick a component representing this particular protocol or data conversion, or why did you do this or why did you do that? So the rationale for describing that. Another very sort of kind of the next step in some of our architectural understanding from a research perspective came from from Mary Shaw and David Garland in 1996. And they wrote a book called Software Architecture: Perspectives on an Emerging Discipline. And that book, for many years, up until recently, was sort of the canonical software architecture text that was taught at the university and graduate level. And the contributions out of that book, I'll state basically, in my opinion, are basically the first identification. So they build upon Perry and Wolf's definition of software architecture, form, elements, and rationale, except they sort of decompose the elements into more than just components, more than just the units of computation in your system. They basically argue that, basically the way components in a software system interact, or something called connectors, which are models of the interaction between software components, they argued in their book that connectors should have a first-class status in software architecture, that the way that the interactions occur is really important for them. So we'll discuss some of that here sort of in the remainder of the slides today. And then finally, if you're thinking about fundamental software architecture research, Philippe Crutzen, who's one of the folks behind the rational unified process, was heavily involved in things like rational rows and other things. He published a paper in 1995 called the 4+1 Model View of Software Architecture. That's another paper that's in which he's basically trying to think, how do we model software systems effectively? What types of things should they have in terms of their elements? And his definitions are very consistent with Perry and Wolf and with Shaw and Garland. Where Crutzen sort of added something is he stated, there's a lot of aesthetics to software architecture. Software architecture, what might be a good architecture to me, where I'm maximizing some particular properties, extensibility, composability, reliability, may not necessarily be a good architecture to you, right? You may care more about its capabilities in terms of data conversion or its flexibility in terms of the interaction protocol or things like that. So the same two software architectures, though they may be similar in cardinality and size, and eventually when we get down to code or implementation, may be different to other people based on their sort of user-defined quality and their perspective on that. So Crutzen sort of introduced this notion of aesthetics that's really sort of important there. Sort of another emerging and building upon philosophy for software architecture came out of Medvedevich and Taylor. And where they sort of built on is they were building on sort of Shaw and Garland, the notion of, and Perry and Wolf, the notion of components and connectors. They built on Crutzen having this sort of aesthetic capability. Medvedevich and Taylor basically suggested software architecture boils down to the following canonical things, and that's going to be the definition that we use here in the class, and that's the thing I sort of want to convey to you because it's consistent with the other definitions, and it's pretty much kind of what we're doing today. Software architecture consists of the components, which are the units of computation in the system, right? The components may compute on things, they may maintain internal state, we may have components for data processing, we may have components that basically are responsible for conversion of things, for sending information. Connectors, which are effectively the way that components interact, request-reply protocols, event-based, publish-subscribe interactions, implicit invocation, these types of things. How are the components interacting amongst one another? And how do other connectors interact too? Sometimes you have connectors which interact with other connectors. Pub-sub is a great example of that, or request-reply or federated protocols. So we've got components and connectors, and then we have configurations, which are arrangements of components and connectors, in other words, your architectural topology, and any rules that sort of guide that composition. Okay? This component may be connected to this connector only. Two components may not be able to be connected to one another without a connector in between them. These two components can never communicate because there's no path through the topology of the architecture for them to communicate, so on and so forth. So the core definition, sort of building upon this, of software architecture that we're leveraging in this course, and that's sort of defined in kind of this newer book on software architecture that's sort of rapidly emerging as the standard textbook, is this book from Taylor, Medvedevich, and Dashafy on software architecture. And basically, in their book, they're discussing architecture as the following in terms of the definition, and it sort of builds on this. They're the principal design decisions about a software system. Right? So when you're thinking about your big data software system, what are the principal definitions that you're thinking about there for the design? And what makes a decision principal? Well, building upon sort of what we're learning about in the prior slides, a decision that makes it principal might be it affects one of the core architectural elements. It's related to some component, some computation in the system. It's related to the interaction, maybe. Maybe it has to do with the implementation, but it's so important because it represents some sort of load-bearing wall or a bottleneck in that implementation. Maybe it has to do with system evolution. Maybe it's a component we're going to want to switch out later, or it's a decision or a principal decision that is going to have some impact on the way that we sort of further evolve the system after we initially develop its code. And then there are others. Okay, so these are various examples of sort of what makes a decision principal. And as you can tell from these various examples, it may be dependent on different stakeholders in the software system, right? Your manager may have a different perspective of what represents a principal architectural decision than, say, your buddy tester developer. Okay. What are some sort of examples, of software architectures? Here's an example. This is a very popular content detection analysis toolkit called Apache Tika. Tika has been referred to as the digital Babel fish. I'll be talking to you a little bit about Tika in one of my further lectures here in the summer school. Effectively, what you can think of it as a small library that handles identification of file types, extraction of text and metadata from those file types, and then identification of language and potential translation of those language. Tika here, if you're just thinking about it in the context of software architecture, represents a number of components. I know that there are components because the nice person that made this diagram for you guys, me, put in a legend for you that states when I see a box here in the diagram, that represents a software component. And what are those arrows between the software components there? Well, there's different types of arrows. One has a dot or some type of dashed lines on it. One is like a solid black line. What do those mean? Control flow is this sort of dashed arrow. Control flow meaning the transfer of control from one component to another. Data flow is a black line. That's how data flows between the components, okay? I see something here called a registry or a repository that seems to be represented by that sort of familiar database-y shape, and so on and so forth, right? So regularly, software architecture is described in this way. You'll notice I haven't stated what programming language Tika is implemented in. I haven't stated, what sort of physical host this is deployed on. Is it put on your MacBook? Is it, are you putting this on Windows? Is it in a virtual machine? All I've sort of discussed the architecture at is at the level of these components, the connectors, which represent in these diagrams those arrows, control and data flow interaction amongst the components, right? And potentially some other meaningful or important annotations here that are present on the diagram, right? So this is a common way to represent software architecture. Now, thinking about this, if we built a whole bunch of these sort of content detection and analysis toolkits, we may find that our architectures, after a while, may look the same. They may use familiar components. You may use some type of language identification component. You may reuse or use some similar text extraction parser or some type of component for that. So over time, what we find typically in domains, and you find this in the domain of big data too, is that an architectural style or sort of emerges, common sets of things like components and connectors. And we'll talk about that. Architectural patterns, which are kind of common arrangements of these things with a little bit of the information left unspecified, they start to emerge. A commonly used maybe vocabulary for talking about architectures within this domain start to emerge sort of as well. So architectural styles boil down to commonly used sort of components and connectors and potentially their types or their classes that you see in a family of software systems built in a domain, normally across many years. Okay, it takes a while for software architectural styles to emerge. Some examples of them are things like peer-to-peer, right? In a peer-to-peer software architectural style and in software systems that implement the peer-to-peer style, we know that there's one component type. There's a peer, okay? And we may instantiate many of those things, but effectively we know that the type of component is a peer. It maintains some internal state, potentially. We know that peers communicate directly with other peers, okay? So the connections, and typically in an arbitrated way, through some initial interaction in which they locate all the other peers on the network, and then those peers' addresses or some root set of them which forward along communication to other peers, and so on and so forth in this sort of organic way. So we know a lot about a system simply by stating it's a peer-to-peer system, right? We know about its components, its interactions, and things like that. client-server, REST, layered. These are all other examples, okay, of software architectural styles. Think about it. I have a question for you guys to ponder here while you're learning here in our summer school. What types of architectural styles do you regularly see emerge in big data systems? Okay, are they combinations of these styles? Like, do you ever see a system that's strictly peer-to-peer or strictly client-server, or do you see ones that are more hybrid? Okay, and that's sort of an open question. There's no correct answer to that, but just sort of think about that while we're talking. So when I think about architectural styles, I like to think of styles as things like ingredients, if you're thinking about things like ingredients and recipes and food and stuff like that. And I do a lot, right? I'm a hungry guy, you can see by my stomach. I tend to think about food a lot. So architectural styles, think of them as sort of the ingredients in your recipe, right? Like what salt, or I need pepper, or I need vegetables, or I need carrots, or this or that. Architectural styles are more sort of ingredients, okay? So you might have heard, if you think about software architecture too, things like patterns, code patterns, if you've read the Code Patterns book by Gamma and things like that. Patterns you might have heard in terms of things like model view controller, or three-tiered pattern, or sense compute control. Architectural patterns are typically lower level than architectural styles, and what I mean by lower levels is that styles are mostly, like I said, think ingredients, right? So patterns take us closer to the actual implementation of software. Patterns may tell us, yes, there are these particular styles of components or connectors in our software system, and they may tell us basically that we arrange them in a particular way and they communicate in this way, leaving sort of outside of the box for that some information to be specified. We arrange in, for example, a three-tiered pattern. We have three components and three component types. We have a sort of UI or presentation tier. We have a logic tier, sort of that the UI and presentation tier communicates with, and then we have some back-end data tier, or component, or whatever you want to call it. So we know a lot about a system too. We know even more than a style by talking about patterns, okay, for that. And so I like to think of patterns more like recipes, right? We may take the ingredients like that we have from styles, salt and pepper and things like that, and vegetables, and put them together into a bolognese sauce, okay, leaving for you to specify in that if you want to make a variation on the amount of salt or the amount of pepper, or whether or not you like carrots in your bolognese or not, or whether you strictly like things like celery or things like that. So it takes us closer to sort of the implementation a pattern does, but it doesn't prescribe or provide everything, okay? And finally, we're going to wrap up this first part of the module just talking about reference architectures, which were a term that was originally coined in the architecture domain by Will Trash in a paper in which he was talking about reference architectures and domain-specific software architectures in ACM Software Engineering Notes way back when in 1995. And Trash basically said that reference architectures have sort of three common things to them. They've got kind of common architectural styles and patterns found in a particular domain, like grid computing or big data or avionics. They've got reference requirements that drove the sort of derivation of those components, those styles, those patterns, and things like that. And then they typically have a domain model or a common vocabulary for talking about systems and data and components within that domain. Okay, so domain-specific reference architectures are typically or domain-specific software architectures are typically reference architectures for a particular domain, like for avionics and so forth. So we use these sort of interchangeably for that. Examples within big data, you might think about things like Hadoop as being a reference architecture, okay, for a particular domain. Common instantiation of components and connectors and things like that. You might think about systems like Globus, which was very popular, many years ago, but still has some popularity and remains that way today, especially with things like Globus Online and so on and so forth. So that represents the end of the first sort of 10 minutes, not 10 minutes, the first part or module here in our big data fundamentals. So we'll move on in the next module talking about some advanced architectural concepts in terms of architectural modeling, architectural visualization, and so on and so forth.